Okay, so in the last section we had looked at sound as longitudinal mechanical waves. And with regard to sound, we have covered so far the concept of interference, beats, and harmonic modes or organ pipes. So all this we have discussed. So we have seen same frequency waves superimposing. They create such that the net amplitude becomes the phasor sum of the amplitudes of the two individual waves. So this is the formula for phasor addition of amplitudes. Okay. Then for beats, we saw that there is superposition of waves of slightly different frequency. So the important thing here is that if F2 is equal to F1 plus delta F should be less than equal to about 5 hertz. And in their case, the superposition results in a beat frequency equal to the difference of the amplitudes. Whereas the average frequency heard is the arithmetic mean of the two individual frequencies. Okay. Now about harmonic modes of organ pipes, we are discussing there are two types, open and closed organ pipes. Okay. So there are a few additional terms I want to discuss before we move on to the next part. So we had seen in the case of open organ pipe. So it is open at both ends. So both ends of the organ pipe act like nodes, pressure nodes for the harmonic mode pattern. So we have for fundamental, for first overtone, for second overtone, like that in general for nth overtone. Now here in this formula, this 2F0, it is called the second harmonic. of the fundamental. In this 3f0 is called the third harmonic. So whichever multiple of the fundamental frequency is, that is called the harmonic. So the nth overtone mode has a frequency equal to the n plus 1th harmonic of the fundamental frequency. So this is a general formula. So just make a quick note of this term called harmonic. In any mode or any modal frequency, if the frequency equals to some multiple of the fundamental, then it is, if it's the nth multiple of the fundamental, like n times the fundamental, then it is called the nth harmonic. So that is why the first overtone mode has a frequency equal to the second harmonic. The second overtone mode has a frequency equal to the third harmonic, and so on and so forth. The nth overtone mode has a frequency equal to the n plus 1th harmonic. So that is the formula that we have for the harmonic series or the overtone series of the open organ pipes resonances. Okay. We'll also discuss closed organ pipe next. Okay, now when it comes to closed organ pipe, so you'll see that it has a different formula and a different kind of a series. So first of all, as you know, for a closed organ pipe, it has one end closed and one end open. So the closed end acts like a pressure antinode and the open end acts like a pressure node. So here the fundamental frequency has the situation that the distance between the two ends is quarter of the wavelength. Okay, so that's for the fundamental. And the first overtone, this becomes 3 by 4L because the length of the pipe becomes 3/4 of a wavelength, or lambda becomes 4L by 3. So the first overtone mode has a frequency equal to the third multiple, or what we call the third harmonic of the fundamental. So this is the kind of series where only the odd harmonics exist. The even harmonics do not exist. So second overtone mode has a formula for frequency given by this, because in the second overtone mode, the length of the pipe becomes equal to 5 lambda by 4, or lambda becomes 4L by 5. So the second overtone mode is the fifth harmonic of the fundamental. Like this, in general, this series progresses. When the nth overtone mode, we have this situation. So the formula for the frequency of the nth overtone mode is the 2n plus 1th harmonic of the fundamental. So that is the formula for the modal series in the case of the closed organ pipe. So first overtone mode has a frequency equal to third harmonic of the fundamental. Okay, so it's just about the terminology, understanding what is overtone and what is harmonic. So overtone is just a sort of index which tells you the member of the series, starting from the fundamental, the next higher frequency, the next higher frequency, and so on and so forth. Okay. Whereas the harmonic is not to do with the which member of the series we are talking about. It's not an index, but the harmonic is the multiplicative factor that we use on the fundamental to find the frequency of that particular overtone. Okay, so that's about the modal series. Now, one final term that you should know is the concept of end correction. It is applicable in case of resonance column experiments. Where we could be testing the resonance that air in an open organ pipe column can make with respect to a particular source of sound, like a tuning fork. So we can test that resonance by pouring water up to a certain level. So the original length of the pipe was L. Now this length becomes, let's say, X, where X is equal to L minus H. So we can manipulate the height of this. Okay. Now, if we bring a tuning fork, So the length of the air column can be manipulated. So at resonant condition, okay, the frequency of the tuning fork will be equal to the frequency of one of the natural resonant modes of the air column. Okay. So by manipulating the height of water in the tank, in the open pipe, okay, we can manipulate the length of the column of air, that is manipulate. So this becomes a pressure node, this becomes a pressure antinode. We can manipulate the value of x. So if resonance occurs in the resonant condition, the frequency of the tuning fork will be equal to some member of this series, like this. It will be the nth overtone mode of that particular air column. So this is the formula for resonance. Okay. Now, in reality or in practical physics, the pressure node at the top, which is the open end, actually occurs slightly outside by a distance delta x. So this distance delta x is called the end correction, and that end correction is given by the formula 0.6 r, where r is the radius of the cylindrical pipe used. Okay, so effectively what happens is then this formula is, it is corrected. So incorporating the end correction, the effective value of x becomes like this. And the resonance condition becomes that frequency of the tuning fork should be some odd multiple of the fundamental frequency where we will replace this with effective x now. Where the value of effective x is this. So this is all about the resonant column experiment.
Sir, why does it occur? Why is the node slightly outside?
That occurs because of the cylindrical nature of the tube. The kind of standing waves formed inside are not perfectly one-dimensional actually. They have a cylindrical three-dimensional shape, and because of that distortion in the shape, the node comes slightly outside. But the mathematical modeling of that three-dimensional standing wave is like far too complex, so it's not in our syllabus. So we just treat it like an experimental fact. But when you do the experiment, the effective value of length from the various measurements you will do in resonance condition, there will be a bit of error in the end, and that error delta x or the this thing end correction, it has a correlation with the radius of the tube you are using or the radius of the pipe you are using. So the smaller the radius in comparison to the length, the less significant that end correction becomes. Okay, is the point clear? Okay. Now the last thing in sound is Doppler's effect, which is really a very simple formula which is applicable for the phenomena of a slight alteration or shift in frequency heard when there is relative motion between the source of a sound and an observer. If the source is moving or the observer is moving or both are moving relative to each other, then the frequency of sound heard is different than the frequency of sound emitted. It can shift in such a way that a larger frequency is heard, or it can shift also such that a lower frequency is heard, depending on the type of relative motion happening. Now, this is very like evident from everyday life. For example, if you're standing on a platform and a train engine is basically blaring its horn as it is moving past you at high velocity on the platform, you will hear that there's a sudden shift in frequency as the train engine was approaching you. So the source of sound was approaching you. You would be hearing a frequency which is higher, okay, and therefore a sound which is higher in pitch. And as it goes past you, the engine, the velocity changes from an approach to a separation velocity. So there's a sharp contrast, and the frequency dips, okay, because the source is now having a separation with respect to the observer, which is you standing on the platform. So that is a classic example of the application of Doppler's effect in a practical situation. So we will develop a couple of simple formulae to understand how this works. So Doppler's effect is about the apparent shift in frequency of sound heard. When there is relative motion between the source and the observer. Okay, so for example, the first situation we'll see is when the source is in motion, okay, and the observer at rest. So here also we'll see different situations. So suppose we have a situation where the source of sound generating sound at a certain frequency f. Now this source is moving with a velocity which is directly towards the observer or the detector of sound. At rest. There's the source of sound of frequency f which is at rest. Okay. And if the sound waves emanate